All right, in section 5 of module 1, we're going to look at increasing and decreasing functions. So if you think just in general what an increasing or a decreasing function is, a function in general is increasing if it's going up and is decreasing as it's going down. It's constant if it's just flat. Now, the official definition says a function is increasing in an interval, AB, if for all values in the interval, if for all x values c and d in the interval, if c is less than d, then f of c is less than f of d. So kind of a long, complicated definition to essentially say this, is if I have some interval, a to b, and let's say the function is going up in that interval the whole time, so it's increasing. That means no matter what 2 points I pick in this interval, let's say I pick this point, which is c, and this point, which is d. Now, I think that you can see that c is less than d because it's to the left of it. Then the functional value, which is just the y value, then f of d should be bigger than f of c, which it is. That's why it's increasing. Now, if it's decreasing, it's the exact opposite. If the function is going down, if c is smaller than d, then f of c is bigger than f of d because it's going down. So it's just the opposite. And in a constant function, all the values in that interval are the same. So all the functional values would just line up to be the same number. Now, what we typically like to do with this is we like to state where a function is increasing and decreasing. And like most things in math, when you're asking where something is happening, we're always going to use the x values. Now, we're going to obviously have lots of x values because it's going to happen in different regions, so this is going to be expressed generally in interval notation. So if I look at my first example here, I have this graph of this function, and it says I want to find the coordinates of any local max or minimums, and then I want to state where the graph is increasing, decreasing, or constant. So first let's talk about local max and local min, which we've talked about before, same as relative max, relative min. So I see a local max where it kind of reaches this peak up here. So there's a local max at x equals 0.04, and that's going to be of 6, so y value of 6. As far as minimums, I see a local min down here and a local min down here. So I have a local min at, the first one is x equal negative 2.2 of negative 9.5. And I have a second local minimum at x equal 2.9, again, using the x value for where it occurs. And that minimum value is going to be of negative 24.1. Now, the second one is actually an absolute minimum because that's at the very bottom of the function for the whole domain. There actually is no absolute maximum because this thing is going to keep going up forever and ever and ever. So now let's talk about where it increases and decreases. Now we can kind of very informally see where it's going up and where it's going down. So in this region, the function is decreasing because the y values are getting smaller. And then it's also decreasing in this region. So it's always decreasing because this function is going up forever, but that function is always decreasing throughout its domain. So if I want to know where it's decreasing, it starts decreasing at negative infinity to negative 2.2 because that's where it's going to stop decreasing. Union, because we're going to have another area, so we have that first area where it's going down, and the second region it's going down is going to be from 0.04, that's where it starts, and then it stops at 2.9. So those are the two intervals where the function is decreasing. Now you notice I use parentheses on all these because you never really want to use brackets for increasing, decreasing, because those are kind of the change points. All right, for the increasing part, you can see it increases in this area. And then it also increases in this area. So the increasing intervals, that first one, that little part, is going to start at negative 2.2 to 0.4. Again, we're going to make sure that we're only using the x values when we're listing our increasing and decreasing intervals. So negative 2.2 to 0.04. And then again over here, it's going to increase from that 2.9, which is the x value of that local minimum, absolute minimum, and then all the way to a positive infinity. And that's the x value infinity, remember, because we're always listing the x values. All right, so we're going to look at a couple more examples of increasing and decreasing functions. So here we have some kind of cubing function. So the first thing I'm going to do is I'm going to try to figure out where these turning points are. So this point up here and this point down here, where it's changing from increasing to decreasing, because that's going to be very important when I start to write my intervals. Now, it's not an exact point, so I'm going to approximate in this case. So I'm going to approximate this minimum to be about negative 1.7, and then comma 10. And this one down here I'm going to approximate to be 1.7 and negative 10. Now, this doesn't necessarily have to be what they are, but we'll just approximate them. And if it's not given to you in your graph, the best you can do is actually approximate. So we'll do increasing first. So the y values are increasing in all of this area up until that point. So basically forever. And then here it's increasing again at this point. So we have two intervals of increasing. So the function is going to be increasing. I'm going to start at negative infinity, because that's the smallest x value it's increasing, all the way up to negative 1.7, which is where it stops increasing, and that's at this local min here. Union, because we're going to have a break in our thing. And the next one's going to start at 1.7 and go to infinity. So negative infinity to negative 1.7, and then 1.7 to infinity. Now, decreasing regions, there's only this one. It only decreases between these 2 points. So the decreasing is going to just be between those two x values. So decreasing is going to be negative 1.7 to 1.7. And again, we're never including the local min, local max. We're just putting the intervals where it's increasing, decreasing. And at those changing points, it's not really increasing or decreasing. So we just leave it with the open parenthesis. All right, if we look at the example down here, we have similar kind of things where we have to do. The first thing I noticed about this graph is it has these arrows. So remember, this is going to keep going up forever on both sides. We'll just kind of assume that happens. So again, I'm going to try to label some of these local max, local min. So this one I'm going to assume is 2, negative 15. This one over here I'm going to say is negative 2, negative 15. And then up here, it looks like the y-intercept is the local max at 0, negative, or positive 9. So if we look at this graph, for increasing, it starts off decreasing. It's going to increase starting at this point, from there and up to that point. So this area right here. Then it's going to take a little break, and then it's going to increase again here. Forever and ever and ever. So the two intervals it's going to be increasing, looks like it's going to be negative 2 to 0. Again, we're using the x values, union 2 to infinity. Function is going to be decreasing on a couple intervals. It's going to be decreasing here, of course. No constant intervals in this one again. Decreasing here. So we're going to have two intervals of decreasing as well. So it's going to decrease from negative infinity, the smallest x value you could ever think, to negative 2, union, and then it's going to be 0 to 2. That second interval just right here. All right, now we're going to look at a couple other functions. We're going to be graphing some functions, again stating the intervals where it's increasing, decreasing. Now these, I could have just given you the equations because these graphs I created were on Desmos. There's a video on how to graph with Desmos and find these local maxes and mins if you missed that one. But all I had to do is just really click on this bottom point and this kind of ordered pair appeared, so I can kind of have that to base my increasing, decreasing intervals. So this graph starts by decreasing, so it's going to decrease to there, and then it's going to turn around and it's going to increase to there. So this parabola only does really two things. So the increasing intervals are going to simply be 0.75, which is that local minimum, to infinity. And then the decreasing, it's going to be decreasing on the beginning of its domain, which is negative infinity, all the way up to 0.75. So again, nothing much different. The only thing different is if you give this equation, you may have to generate the graph from Desmos or your TI calculator, whatever graphing utility you are using. So let's look at one more example. We have x cubed plus x squared minus 4x plus 1. So when I graph this on Desmos, you can see I have this kind of graph with a couple turning points. We have this local max of negative 1.35, 5.879, and this local min of 0.869 and negative 1.065. So it looks like it's going to increase on two intervals. It's increasing here, and it's increasing here. So those two intervals of increasing are going to be negative infinity to negative 1.535 union 0.869 to infinity. And of course we got this one little interval of decreasing in the middle. It's just going to decrease at this little area right here. So it's going to decrease from negative 1.535 to 0.869. So a little bit about some properties of functions and how it is increasing and decreasing. If you have questions, please let me know.